I'd like to start by welcoming all participants to our presentation. Then I'd briefly like to introduce us. My name is Tamara Hofmann. I'm a consultant at ProStep AG. I will give you a brief introduction to the problem at hand. Then I'll hand over to my colleague Anna Wagner. She's a senior consultant at ProStep AG. She will talk a little bit about the methods, concepts, and our ideas for solutions, which we applied in the POC we carried out for Porsche. René Bielert from Porsche AG will give us more detail on this and delve into the POCs. He will also give us some insight into what the current needs and problems in the industry are. So I will start by addressing the challenges, which many of you will be familiar with from experience. First, the question, why do we even need the digital thread? Throughout product development and the entire product lifecycle, of course, many domains come together, which really have to work together collaboratively. Individual domains use their proprietary tools adjusted for their use cases and tasks and work with these. Data is stored in these tools, and during collaboration, to get a complete overview, I have to make information available between applications. Of course, depending on the area of application, I need different information, and this is stored in my tool. As a result, I may have more information on one product in one tool. I may have stored the data differently. It may be interconnected slightly differently depending on the task. Now, if I want to transfer data from tool B to tool A, then currently, as it stands, usually I have to edit the information, download it, put it into the other tool and integrate it. This requires considerable integration effort because I have to map data, copy data, and then integrate it. This causes the problem as well of redundant data. Redundant data increases the risk of having outdated information because this process is often manual and it's not usually automatic. So I don't realize when I'm using tool A that data in tool B has changed. Now, it may be the case that I don't need to be able to edit data in tool A. Instead, I just want to integrate the data because I want to check information, because I need information from tool B for what I'm doing. In this case, it would be sufficient to just reference and visually integrate this information. By doing so, I would avoid having to store data redundantly. Now, let's look at the information modules that occur in systems engineering via the V model. Let's start with the stakeholder analysis. I have my requirements, requirements management. I carry out a decomposition of my requirements and split them up according to discipline or according to function. Moving through the V model, I have my system design, I have integration, I have implementation, then of course I have tests, and all this generally culminates in tests to SOP. Of course, I don't just have this one route through the V model, but in the process, I'm also confronted with the problem or challenge that many different disciplines have to interact with each other. I don't just have a software product or a purely hardware product. It all has to come together and to be interconnected in terms of design and analysis. With MBSE, I take the approach that I say, I have a system model where all of these domains are grouped. But of course, with a model-based approach, I also return to the specific disciplines and have different models interacting with each other, which obviously generates a lot of data that needs to be interconnected. Now, then I come to validations and tests, and then I'm faced with questions. Have I designed the system correctly? Have I even modeled the right system to fulfill the stakeholder requirements? Now, what kind of data network is useful? Here, we often use the analogy of a perfect secretary's office. I have a secretary, I go to the organized office and I make a request. I say I need the E-bomb structure from the Mars rover. My secretary is good, they're very well organized, and they know that the information on Mars rover can be found in the green area. Perhaps my secretary is excellent. In that case, they'll also know that information on E-bomb structure can be found in these two files, in these two drawers. Now, I might not be interested in the entire E-bomb structure, but would rather just have the information on the chassis. Most secretaries will have a few issues here. They might not know exactly where information on just the chassis can be found. Now, if I have an excellent secretary, then they'll be able to find me the right files with the information on the chassis. Now my question gets even more specific, and I say, in fact, I'm only interested in the screwed components. For most secretaries, alarm bells will now start ringing. This is very specific, and most secretaries would have to know a little bit about the files themselves. So if my secretary is not just excellent, but has also studied mechanics, then they might be able to help me. They then will be able to say, no problem, these are the few documents that you're looking for on screwed components. But this obviously also causes a problem. The perfect secretary is in fact better qualified than the engineer. Then the question is, what is my role here at all? Unfortunately, we don't have a perfect secretary at all points that we would need them. So the question is, how do I get my data effectively across disciplinary boundaries? Our solutions for this will now be presented to you by Anna. She will tell you a little bit about our ideas and our solutions for this problem. The basis of our pilot project is a flexible data model. This data model is built on 3 levels. The first level is domain ontologies. These domain ontologies represent expert knowledge from different domains, such as mechanical engineering, systems engineering, or processes from a business perspective. These domain ontologies contain complex logic. This is why they are highly specialized, and it is difficult to reuse them outside of the original domains. To enable reuse, there is a second level, a domain-independent perspective. Here we have the general descriptions defining an independent taxonomy. For example, that there are different models, and these can be practical models or theoretical models. Accordingly, these concepts also have weak and logic-free connections to create a thin layer that is easy to reuse, to which we can then refer from our domain ontologies. Moreover, we have the generic core ontologies that we use as a sort of glue. These core ontologies are free from taxonomies. They describe cross-domain logic. As a result, they enable us to group and view multiple domains in a use case and to abstract common concepts, facilitating powerful search queries. Our listeners might have understood that we do speak a lot about ontologies with our flexible data model. That's because ontologies are the technological basis of our pilot project. Why? Well, mainly because we can describe data-integrated logic with ontologies. Let me explain. The basis of this data-integrated logic is that relations can be strengthened by logical axioms. Here we have transitive relations or logical chains. I have an example for you with 3 people, A, B, and C. These 3 people are connected to each other via relations. Transitive relations are relations that span several steps. One example would be that A is B's colleague and B is C's colleague. We can assume that my colleague's colleague is my colleague, which is usually the case unless I have several jobs. Then this relation would be transitive. By using ontologies to represent this, a machine could then infer that A is C's colleague. Logical chains work in a similar but more powerful way. Here we are working with different relations. An example here would be that A is B's brother and B is C's father. Humans can conclude that A is obviously C's uncle. By defining the relation is uncle of in a chain of is brother of and is father of in exactly this order, then an algorithm or a machine can also come to this conclusion. These sorts of axioms can be attached to relations or also to classes. With classes, you can predefine aspects and values of types. One example is an elephant. We know an elephant has big feet and a relatively short tail with 3 brush hairs at the end. We associate elephants usually with thick grey leather, with big ears and a long trunk. So, whenever we see an animal in real life or in a zoo with these features, then it is usually very clear for humans that we're seeing an elephant and not a zebra. By serializing and formalizing this in the form of an ontology, a machine can also infer this. This inference, however, is merely the result of adding already available information, which was implicit in the data. We can only add more information. We cannot exclude anything. This is the open world assumption that applies for ontologies. For a closed world assumption, with strict rules, such as an elephant cannot be pink, other technologies are required, such as shackle. All in all, however, ontologies and shackle provide a standardized vocabulary to describe logic. This means that I can use a very simple, unchanged vocabulary to cover all the use cases on this slide. It also means that I don't have to hard code to analyze my data or to receive any additional information. Instead, I can use a standardized algorithm that can analyze all these logical axioms. And it is for this reason that we don't just refer to ontologies as being machine-readable, but also machine-understandable. Another approach for our pilot project was that we used a modular design. This means that we formed topic clusters that covered the different areas of our use cases in the V model as well. These topic clusters were as precise as possible. This means that these modular ontologies can be considered and reused in different use cases from different perspectives. Moreover, we also connected already available ontologies to the ontologies that we generated, to also be able to use search algorithms that had already been implemented, such as those in search engines like Google. During the pilot project and the POCs, it quickly became clear that, for example, these 5 ontologies from the portfolio we generated were not sufficient, so that we generated further ontologies, for example, for the IT development or material descriptions. Because we chose this modular design, it was very easy to add additional ontologies. As a result, it's possible, and we're sure, that we are not just able to represent both the POCs, but also the entire process chain of the V model. Now, what does this mean for a digital secretary's office? It means that we have formed the basis for making interconnected and machine-readable annotated data available, alongside the connected source systems, of course. Together, this creates the perfect digital secretary's office. So I can get started with my request. I need information on Mars rover, and particularly the E-bomb structure. Thanks to the annotation, the digital secretary's office can quickly establish which areas cover data on the Mars rover, and more specifically, the E-bomb structure. Here you can see that it is not only the information available in the overview graph that is retrieved, but also new and more direct connections can be established, thanks to the logic embedded in the ontologies. When I make my request more specific and ask for information on the chassis, this digital secretary's office can also jump off at specific nodes and look in the source systems. Then, additional information can be extracted. This has the advantage that the screwed components are not just found in the overview graph, but can also be found in the source systems themselves. This is because the heterogeneous data is annotated. Another advantage is that this communication is bidirectional. I can communicate with my secretary's office when I've changed the data. Here, my first input would obviously be that I have all of my domain-specific data available. Then I can focus my data input range on this limited range, the E-bomb structure within Mars rover. I can then further specify what area or what specific element has changed. Then I can transfer the changed data. I can use Shackle to check whether all necessary information has been submitted. For example, perhaps a person responsible has not been entered. In this case, the Shackle constraints, shape constraint language, can establish that there is a violation and the data consistency and quality cannot be ensured. For this reason, the Digital Secretary's Office offers a major benefit. By checking the data before introducing it into the data pool, the data quality can be increased. As a result, we can ensure that less redundant and incorrect data is present. Now, René will explain to you how this Digital Secretary's Office can be used at Porsche, and which challenges in particular the industry hopes to overcome.
The automotive industry is currently dealing with a whole number of disruptors and is shaken as never before, probably seeing the most radical changes since coaches were motorized. And quite similar to here, we're not only dealing with electrifying our sports cars, but also digitalization. As we can see, that doesn't necessarily make our lives any simpler, but partly more complex. So the growing number of networked vehicle functions, but also interaction with the ecosystem, increasingly augments the complexity of the vehicle and therefore also the development process of the vehicle. With classical structures, that's hardly manageable, so at this point we need an organizational and procedural change, which is reflected mainly in systems engineering. At the same time, digitalization does not stop at our development center in Weissach itself. Here as well, we have seen dramatic changes in the development process itself. Besides the organizational change in systems engineering, we also need increasingly model-based methods. Particularly CAD and simulation models have long been standard, but now in the other systems engineering areas and processes we also need model-based approaches, and for that, amongst other things, we need IT software to accomplish this. So that not only the process and our development and our cars are subject to radical change, but at the same time also our IT. Just to mention a few buzzwords: AI, end-to-end processes, digital thread, or also cloud. In order to cope with this complexity, particularly in development, it's increasingly important for actors to communicate with each other. Before, it was sufficient for the module development only to communicate every now and again with the software developer, but now it's become a common practice for the colleagues to have to communicate at least on a daily basis. And that's where the whole problem starts, because normally there is a language barrier between the two development disciplines. Very often, the module development only understands very little of the software problems described by a software engineer, and at the same time, the software engineer doesn't really know much about spatial collision, for instance. In order to enable collaboration, we need various IT software tools to be able to work together interdisciplinary. It's important that in each individual discipline we use specialized tools. Generally speaking, it does not work with Visual Studio if you want to design a module. Just as little would I think of trying to use CATIA software to program. So it's a highly domain-specific world I'm trapped in, and at the same time, the probability that there will ever be this one tool that can do absolutely everything is rather low, particularly as tasks are becoming more and more complex and more difficult. So it's incredibly important for these individual disciplines to be networked with each other and at the same time result in an integral data model. At the moment, generally, and still, we solve this problem with comprehensive interfaces at Porsche. We're networking individual systems. But now we have a second problem. Before, we had to unify the languages and the disciplines, which you still have to do. Now we also have to unite the languages of the tools, that means the data. So we have a problem of terminology doubled. And also, creating too many interfaces is not a sustainable solution, particularly as we solve the terminology problem, but generally speaking, we do not document things, particularly not in a model-based way, so that we can actually use the data subsequently. So we have a rather elaborate and not sustainable process, which leads us away from the real goal, that is to network all the data together and understand the data. So we miss our goal, and therefore we're not providing the digital twin of our sports cards, and that way at the same time we're preventing even being able to offer or create a perfect secretary. In order to achieve this goal, we need a different concept, and this is hardly a surprise. It has to be model-based, just like our development is increasingly model-based. On the one hand, we model the data object with owl and shackle. On the other hand, we model the business objects, that means the divisional language. And in between, we start drafting generic concepts, just as demonstrated by Anna a moment ago. And that leads to models which are machine readable and machine understandable, and at the same time domain specific and pan-domain. Further, it is possible to connect data, extract data, and integrate data and translate into RDF, so that you end up with one joint common knowledge graph, which contains both the model, the description of the data, and the data themselves. As the model is machine readable, from here, standardization has occurred, and then the process-specific information can more or less be provided in an automated way by models. And that means that a digital secretary can at least be piloted. We have done that in order to prove the concept and carried out two proofs of concept. One follows the V model, that means it's extremely close to development, and one deals with ID development in order to reduce the number of silos as well at the same time. How did we do that? First of all, we carried out workshops with the divisions, and there the data within the divisions were recorded, but also the division-specific languages and the processes. During the workshop already, we started, in this case on Miro boards, to model this information, and subsequently in a second part, we generalized that and summarized it. And in a third step, we really mapped the actual exemplary data in these models. So we took real information from a vehicle project, a slimmed down version, as an example. Using RDF and shackle, it is then also possible for these to be provided in a process-specific way and with minimal effort. Amongst other things, using cloud, RDF, triple stores, and also shackle, we managed to do this quite quickly with a low amount of effort to provide the data and offer the first pilot presentations. But in many points, we're still in our infancy. Particularly, identification of instances within data is still quite difficult. In this concept, generally, we always have fixed IRIs with specific methods, but we did not document how these IRIs were generated, particularly not based on a model. But that's extremely important, particularly as the identification of topics is often domain-specific. A module developer often understands a module to be something different than somebody in production. And then we have various topics where we have concepts, but implementation and proof of concept seem to be too complex, like, for instance, versioning, historizing, and also everything to do with rights and roles, which are extremely important. At the end of the day, we don't want everybody to go to the digital secretary and at the same time simply be given all the data available in Porsche development. That wouldn't be very purposeful. And a final and difficult part, which has very little to do with modeling itself actually, is extraction of data from legacy systems, particularly when the systems are extremely old and do not use modern technology, like for instance streaming or interfaces. And at Porsche, we actually do have quite a few of those in use, amongst others also various IBM host systems running on consoles. So the difficulty in that case is, how can this data gold even be extracted for it to then subsequently, with the technologies using URL, Shackle and RDF, be polished up with semantic to be able to produce a digital twin so that midterm to long term we can actually offer a perfect digital secretary.
That brings us to the end of our presentation. I hope you managed to follow everything. I think you'll be able to download the slides afterwards. Do we have any time for any questions?
The real implementation itself is something I can talk about. It was done by 2 interns effectively, and each of them had 6 months, but they had to work their way into the field first. So I would say both of them spent about 3 months each productively on this topic. But modeling, well, we had about 10 to 15 modeling workshops together with the divisions, which lasted about 1.5 to 2 hours each, and about just as much time for generalization. And then subsequently, a lot of time was really invested to write down and document the models, which is an effort you should not underestimate as well. But it has to be said, we went right through the entire V model once, and from each division and each main process in the V model, we integrated data and models, so that means it's quite a comprehensive proof of concept.